To our course. Sorry. Welcome to our course on federated learning, which is offered. I think you have your. Yeah. Sorry for the little glitch. We offer this course as fully online, but I'm sitting here in the lecture hall with a few students, which is nice. But yeah, you should be able, or you can complete this course fully remote. It's self-paced. We have no mandatory assignments. Yeah, at a glance, this course is worth 5 credits. It's fully online, no mandatory attendance. It consists of 6 modules. Each module has a lecture, which happens on Monday in this very time slot, in the same Zoom lecture hall. But yeah, as I mentioned, we also have reserved a real lecture hall, a very nice lecture hall here at Alto Campus. So if you want, you can spend or follow the lecture also here in the lecture hall, whatever you prefer. And yeah, what else? Yeah, this year, one of the changes in this edition, based on the student feedback, is that we offer additional activities. So one of these activities will be a paper review. So for those of you who are more advanced, so which have already some basic knowledge in federated learning, instead of the assignments, which I will talk about more in a second, you can do paper, you can review papers like current, recent research papers. Yeah, another change in this year is that we have the student project as a mandatory part of the basic version. So the student project involves a peer review. So each one of you has to review 3 to 5 other project reports. This is meant also as a training of the basic, or maybe the most important tool in academia, which is peer review. So you will practice basically a paper submission like for a conference. You could use this also as a test for some conference submission that you are working on, and get feedback from up to 5 other students. Yes, I will tell more about the student project in a second. Yeah, finally, last year we had the student project as the extension to 10 credits. And this year, the student project is part of the 5 credits version, but on a case-by-case basis. So if you did well in the basic version, in the 5 credits version, I'm willing to discuss a potential extension to 10 credits, but the details are to be determined. So this could be, for example, extending your student project more. Any questions at this point? Please ask questions in the chat or here. Okay, so far so good. Yeah, just the outline for today's intro lecture. First, I talk about the prerequisites. So what do I expect from you? What is the starting point, the launching point regarding mathematics and coding? What are the learning goals? What do I want you to learn after this course or to know after this course? Then I will talk about related courses. So I will position this course within broader machine learning curricula. Then I will talk about the course logistics, in particular the schedule. And the final part is then actually getting down to business. So we talk about federated learning and how it evolves from basic machine learning techniques, in particular from regularization ideas. Okay, so the prerequisites for this course, I expect you to be familiar with objects like vectors, Euclidean vectors, matrices, or norms. So if this looks very strange to you, then either you try to refresh your linear algebra skills, or you might consider taking this course maybe next year. So this is really the bare necessity. You should have one course on, or the first course on linear algebra. Then we will use calculus. So you should be somewhat familiar with the notion of smooth or differentiable functions and their gradient as a generalization of the differentiation. Okay, we also use, or we assume that you are familiar with basic machine learning techniques like this expression here, empirical risk minimization, should be not too strange to you. So you should have had some course already where you train machine learning models and validate them. Yeah, and in the exercises, which you will hear more about in the Wednesday session, we will ask you or require you to implement these theoretical concepts that I talk about in the lectures. I talk mainly about mathematical models, abstract concepts, but you will see how to implement them, or you will implement them using Python in the assignments. Okay, so the learning goals, what do I want you to get out of this course? After completing this course, you can model federated learning applications using networks. So maybe some of you have had courses on network models, complex networks, and we use those models to formulate federated learning applications. And in particular, we use those network models to formulate federated learning as an optimization problem. So after this course, you should be comfortable with translating a federated learning applications, a real-world federated learning application, into an optimization problem. And as soon as you have formulated it as an optimization problem, you can try out, or you can try any of the optimization methods you have heard about to obtain federated learning algorithms. So this is a very clean, very principled approach to design federated learning algorithms. We formulate federated learning as an optimization problem, and we apply distributed optimization methods to this problem. And finally, a core component of this course will be key requirements for trustworthy federated learning. You will hear about explainability, you will hear about privacy protection, or how to measure privacy leakage using differential privacy. So you will also get some very basic skills for designing federated learning systems that are somewhat transparent or explainable and privacy preserving, which is one of the key features or characteristics of federated learning. So how to do distributed machine learning by still protecting to some degree the privacy of user or user data. Are there any questions at this point? So how many of you, just let me ask, how many of you have learned about optimization methods or had a course on optimization? Very good. How many of you have heard about gradient descent? Very good. How many of you have heard that gradient descent is a fixed point iteration? Very good. I guess in one of my courses. No, so just as an outlook, we will basically use gradient methods, and we will see how to generalize gradient descent methods by interpreting them as fixed point iterations. This is useful because gradient methods can only be used for parametric models. But you will learn in this course optimization methods that don't require parameters, model parameters. Any kind of model, a decision tree which doesn't have a natural parameterization, you can use or you can use for the federated learning algorithms that we discuss in this course. Okay, so regarding the positioning, yeah, as I mentioned, the bare necessities are a course on matrix algebra. For some reason, this linear algebra course in Aalto is called matrix algebra. So such a course that covers what are vectors, what is a linear vector space, what are norms, and all these kinds of very useful concepts. So we expect that you have taken such a course. Then you should have had a course like a machine learning bachelor course at Aalto, where you learn how to train machine learning models, to validate them and to regularize them. And in some way, this course really takes this one step further. So instead of training one single model on one single data set, you will learn how to train a coupled network of models. And this network of models could be, for example, all smartphones that run a certain app. So a federated learning app, for example. Okay, then you should be familiar with Python, the Python programming language, in particular, how to read in data, how to work with numeric data. And there I found a nice online course, Data Analysis with Python. So We start very slow, so you will have the opportunity to refresh your knowledge. But as I mentioned, I consider these courses and the content of these courses as really the bare necessities for this course. Then what is nice to have, as I said, we use a lot of optimization, or we discuss optimization methods, but I will build it up very slow and maybe from a bit of a different perspective as you hear in this introduction to optimization course. So from my perspective, optimization algorithms are just instances of fixed point iterations. And as soon as you understand the fixed point iteration, you understand the optimization method. Okay, yeah, and then there's also one more advanced course on convex optimization. If you really want to look into, want to do a careful analysis of convergence rates, then I recommend this more advanced course on convex optimization. Yeah, and as a follow-up, so once you happily finish this course, what I found is a course on wireless systems, because in this course we mainly talk about mathematical models. So as I like to say, pen and paper is patient, but when you have to implement these federated learning algorithms in real hardware and really on the physical level, you must at some point use some form of wireless communication link, or you must establish a wireless communication link. And if you really want to dig into the details of this, then there's also an excellent course at Aalto called Wireless Systems. And I also found this course, Distributed and Intelligent Automation Systems, which covers a very important application domain of federated learning, which is the Internet of Things. So a machine learning task, or each machine learning problem corresponds to one sensing device. And you want to train the machine learning models for each sensing devices in a collaborative fashion by exploiting similarities between the datasets. Okay, any questions at this point? Not yet. Here on the chat. Okay, here's a question. What is the difference between 5 credits and 10 credits? Yeah, as I mentioned, this potential extension to 10 credits is decided case by case. So I would suspect that we offer this 10 credit extension only to students which do really well in the basic course variant, in the 5 credits variant. And then it's up to negotiation what you want to do. If you want to expand, for example, your paper review, you want to review another paper and write a report about it to get 10 credits, or you want to extend your student project into a journal paper or something. Okay, then another question. If the course is self-paced, how do we ensure that all are doing the project? Yeah, we'll talk more about this in a second when we come to the course schedule. So there are some deadlines. So it's self-paced, respecting the submission deadlines, of course. So regarding the schedule, we have 6 modules. So the core content is divided into 6 modules. The first module is a machine learning refresher, which we will cover today. And there will be an assignment for each module. So the first assignment will be introduced on Wednesday, again here in this Zoom lecture hall, by teaching assistants. And yeah, then we have a second module, which then starts next week, which is about using networks or graphs to model federated learning applications. Then we will have a third module on federated learning design principle, where you will learn how to formulate federated learning as an optimization problem, in particular as an optimization over a graph or a network. Then the fourth module then builds on this by applying distributed optimization methods to this optimization problem, which then results in federated learning algorithms. Then we will talk about some main flavors of federated learning, which you might have heard about. So we will talk about clustered federated learning, vertical federated learning, horizontal federated learning, for example. And we will see how these are just special cases or special specific design choices for this optimization problem that we will learn in module 3. And the final model, I would say maybe the most important one regarding my preference, it's about trustworthiness. So there we talk about explainability. So we want to build federated learning systems that are transparent to the user to some degree, that are robust. So if some nodes in the network fail, the whole system should not break down. Or if some of the participants in a federated learning system are malicious, let's say cyber criminals from Austria, then we still want the whole system to work well. So this is related to robustness. And of course, this is actually one of the key promises of federated learning, or why it became so popular, in my opinion, is this promise of privacy protection. So we will see that federated learning algorithms don't share raw data, but only derived quantities like model parameter updates. Of course, there's a trade-off. Some information must be shared, because this is a simple, a trivial observation. If there would be, if there would be perfectly information protection, so there would be no information spreading out of a client in a federated learning system, then why should you use it at all? Why should it be included in the federated learning system? So some information must be shared between the nodes. But the question is, which information? And is it sensitive information? Okay, then the content of these models is evaluated in graded activities, because I guess some of you or most of you want a grade for this course. So the graded activities include assignments, where you will implement all these mathematical ideas and concepts in Python using auto-graded Python notebooks. You will hear more about this on Wednesday in the exercise session. And yeah, we will release the Python notebooks around Wednesday. So you will then on Wednesday you can start to work on these notebooks. They are small student tasks which require you to complete code snippets, basically. Okay, then the second core component of this course is a student project. And there I want you to practice the modeling. The modeling is really the art here. How do you formulate a federated learning application, any application of your wish, as an optimization problem? So this is your task then in the project. You must formulate a federated learning application using the concepts that you learn in this course. So in some sense, this course teaches you some instruments or language that you will then apply in the project. So you will use the language to formulate a federated learning application such that your colleagues who peer review it understand it. Yes. Very good. Yeah. So there was a question if the project is individual. Yes. Every student has to submit independent personal project report. There is no group work allowed. Okay. Yeah. And then one change that I implemented based on the student feedback of last year, where some students were a bit, let's say, bored. So they were more advanced and they wanted to really read and understand the cutting edge or bleeding edge federated learning techniques. And for those students, I have now introduced a paper review activity. So instead of the assignments, if these assignments are boring to you, you can look up a list of papers that I have linked here with a QR code. You find those lists also on the federated learning website that I have shared with you via my courses. And yeah, the deliverable or the task of this paper review will be to interpret this paper that you picked using the instruments and the language of this course. So in this course, you will hear about GTV minimization. So that's the name of this optimization problem. And I want then to hear from you in your paper review, what type of GTV minimization does the paper use? Or is it completely different from GTV minimization? You must somehow interpret or analyze this paper using the instruments or concepts that you learn in this course. That's the name of the game. And you have to present your review as a slide talk, and the deliverable will be the slides and a recorded talk. This is like a little conference talk. Should also let you practice conference presentations. And this should be maximum 10 minutes. This is also a bit of a challenge. You must stay within 10 minutes in your talk. Okay, then, so these are the graded activities. You can collect points in these graded activities. The point distribution is as follows. Okay, there's one question. Yes, please ask the questions on the chat. Have a look. There's one question. Is there any intersection between graph learning and federated learning? Yes, we will. So this is already quite detailed question. We will talk about graph learning in the second module, about when we talk about federated learning networks. There, we can use, or we sometimes should use graph learning methods to learn the optimal collaboration pattern between federated learning nodes. Then another question, does the project need to be something new or just an implementation is fine? Well, it cannot be, you cannot reuse a student project from another course. So, but you don't have to invent, actually, we require in the student project that you use some of the methods from this course. So you don't have to invent a new federated learning algorithm. You just, yes, another question? Yes. Mhm. Yes. So the question is, how does the points combine that you collect from the paper review with the points that you get from the assignments? And for this, we have here this formula. So we use the maximum of the points that you get from the assignments and from the paper review. So you can do both. You can do assignments and the paper review, and we will take the higher number of points. Yes, you can only improve. So maybe this answers your question. When I go over the point distribution, so for each of the assignments, you can get up to 7 points. So in total, we have 6 assignments, which makes 47, 47 points, if I'm not wrong. So for the peer grading, you get 7 points. From the project, 51 points. And for the paper review, you get up to 49 points. So yeah, you can improve using the paper review. If you get full points, you get more than if you would do all the assignments. Slightly more. I'm not sure what was the intention there. But yeah, so but the idea is to allow students for which this for whom these assignments are underwhelming, that they just focus on the paper review. They don't have to do the assignments. But it seems weird. Well, penalized if you so the paper review will for sure not be the easy option. Yeah. 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 So the intention is that you can replace the assignments with the paper review. But if you want, you can also do both. But I'm not sure if this is a typo here, this 49 points, and we should have here actually 42 points. But yeah, it's not too big of a difference. No worries. If you're really interested and work hard on the course, you will get a good grade. I'm confident. But of course, we also don't make it too easy because we want to keep you motivated. So yeah, how do we translate the points into the grade? So for 50, when you need to get at least 50 points to get a positive grade or to pass the course with grade 1, 50 to 59 points. Then starting at 60 points, you get a grade 2. Starting at 70 points, you get a grade 3, 80 points for grade 4, and at least 90 points for the top grade 5. Yeah. Is this okay? Does it? Yeah, I think it's pretty straightforward, pretty regular. Okay. About the assignments. So as I said, for each module, we have 1 assignment. 6 modules make 6 assignments. First assignment is about using Python to implement model training, validation, and regularization. Second module, you will use network models using NetworkX library to make a whole network of machine learning tasks. Then you will see in assignment 3 how to solve federated learning as an optimization problem. Assignment 4 is about implementing federated learning algorithms as message passing over networks. Assignment 5, you will look at 2 specific flavors of federated learning, in particular clustered and vertical federated learning. And in the assignment 6, you will study privacy attacks. Think this is about inferring the location of somebody from whom you only know weather predictions. And you will learn how to ensure subjective explainability of a federated learning system. Okay, then about the student project, as I already mentioned, you are free to choose any federated learning application of your choice. There's no limitation, no restriction. You only have to use the tools or instruments from this course. So you have to design and study the federated learning algorithms that we talk about in this course in module 4, I think, yeah, module 4 and module 3. Then you have to write a project report, which is similar to a conference paper. And we will also provide a template for this. So the structure is pretty much fixed. You will get a LaTeX template for this. Yeah, I think we will stick to LaTeX as the document preparation tool. I hope everybody is familiar with LaTeX or willing to learn it. I think it's still the standard typesetting tool in academia, as far as I know. Okay, then, yeah, we have a bit of time. The project only starts after this boot camp. So in the beginning, we have the 6 modules, which are kind of a boot camp. You learn the basic techniques and instruments, and then you can focus on your project, and you have to submit the first version of your report by the end of April. Then we have a 2 weeks peer review phase. So till mid of May, you have to peer review others' reports. And we will still need to decide how many reports you have to review. Between 3 and 5, I think, would be a good number. Yeah, and the final deliverable is a revised report. So you have to revise your report based on the peer reviews, and you have to prepare a response letter. So we will also provide you a template for the response letter where you explain how you revised your report based on the peer reviews. So this should let you practice this basic workflow of paper submission in academia. This is how it works. So you get reviews, you get feedback, you try to address this feedback and submit the revised version. And then the associate editor, for example, me, decides if you sufficiently address the reviewer comments and it can be accepted. In this case, we don't have acceptance or rejections, but grading. So the number of points that you get depend on how well you took into account the peer reviews. Yeah, I just want to point out that we often get the feedback that students don't like this peer grading activity. And we have de-emphasized this peer grading activity to 7 points. But just to point out, we take your peer grading performance into account. So you must do a reasonable job, not just giving best grades as a peer review and no justification. So each aspect of this peer review, we have some 10 to 15 aspects. For example, does the report clearly explain the network structure used or something like this? And you must then justify your peer review. No, the paper didn't explain or didn't describe the network structure. Or yes, the network structure was described in section blah, 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 blah. So it must be reasonable comments that you should give as a peer reviewer. And we will look at those. So if you do trivial responses for the peer review, you might not get the 7 points. Okay, the schedule. What about the schedule? We have the lectures each Monday. So 6 lectures for the 6 modules starting today in Zoom. If possible, I will try to be also present in the lecture hall like today. but by default they're in Zoom, in this Zoom meeting, which you are now currently. Then on the following Wednesday, we will have an exercise session where a teaching assistant introduces the assignment for the module. So for example, on the first two assignments, so assignment 1 and assignment 2 must be submitted by the 17th of March. So we have the same deadline for the first two assignments, which gives you more time for the first assignment and less time for the second one. In order to get into speed, to get used to this submission system. So we use a Jupyter Hub, which you will hear more about on Wednesday. And yeah, we then have the next deadline end of March for assignment 3 and assignment 4. And the final deadline, submission deadline for the assignments is the 14th of April for assignment 5 and assignment 6. Yeah, and this is before then the first project report submission, which is end of April. So this project, you should focus then after the modules, after the assignments. Okay, peer grading until 15th of May, I already mentioned, and the final project submission is end of May, which is also the official end date of the course. I think, yeah, this course is until end of May, running until end of May. Okay, let's see, here we have questions. Then one question, what if someone wants to do more than one project? Will they be graded? Well, if you want to do more, then we could discuss this extension to 10 credits, but by default, everybody does one project. Next question, does ChatGPT use federated learning in its implementation, or only if it requires multiple inputs that federated learning is used? I don't know. I don't know how and if and how ChatGPT uses federated learning. Regarding then another question regarding paper review, is the list of papers exhaustive? No. So I'm also open to suggestions from you. So if you have a cool new paper at NeurIPS that appeared on NeurIPS and you want to do a paper review, please let me know. We can discuss it, that you can use also papers beyond the list that I provide. Yes. Any other questions at this point? A good point. So the question was if there will be exercise sessions for the project work. So when you work then on the project, we might set up some. Yeah, it's not planned yet, but it's a good point. I might set up some garages. Yeah. No. Yeah, it's a yes. That's a good point. So we might set up some 2 or 3 project garages where I will be present in some lecture hall. Very good point. I hope till next week. I'm working on it soonish. Yes. But yeah, in general, so the question was, when will the project report templates be available? I'm working on it, polishing them, and hope to publish it by next week. But yeah, as I said now, I would say for the next 4 weeks, the focus should be more on the lectures and assignments. But of course, you are free to start already now thinking about some interesting and exciting federated learning applications for your project. Okay, so there's one more question. If I have doubts regarding assignments after the exercise session, can we ask through Slack? Yes, please make heavy use of our Slack discussion forum to ask about exercises or lectures, anything about the course. Okay, so yeah, for this course, I really want to emphasize the 2 main ground rules that I have in my courses and that I started to explicitly articulate in the first lectures. So first of all, as a student, as a participant of this course, you must act according to the Aalto University Code of Conduct. How many of you have read the Code of Conduct? No, I have read. I've glanced over it. So it's something we all commit to, like code of conduct for research integrity and blah 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 blah. But it's good to sometimes actually read it. But I have summarized it basically. So the two main ground rules are, as in general in academia, be honest. So this course involves a lot of independent work, completing assignments. I will not sit next to you and check when you submit your assignments using your Python notebook. It's up to you. I trust you that you do your assignments yourself. What is important is you should not steal work of others, ideas of others, solutions of others. Be honest to yourself also, and in particular, indicate or cite any source that you used. So this is rule number one: be honest, and of course, trust is good, and control doesn't hurt. Or how is the saying? So we will randomly select students. This I do in all my courses, which require a lot of independent work. We will use a lottery wheel and randomly select students which are invited to a one-on-one meeting with me and have to explain their solutions, which should be no problem if you did your assignments yourself. You just have to explain them to me. And of course, I expect that you have no problems in explaining, but if I get the impression, and I really, I'm a very kind person, but when I feel my kindness is exploited or abused, it turns. So I will not hesitate to report to the study admission officers, because I want to ensure that when you get a grade, it's really deserved in this course, and I want to combat any gaming as much as I can. Okay, so rule number one, be honest. Rule number two, be respectful. I will not tolerate any disrespectful behavior in this course. And again, if I observe this, and there's really a confirmed case of disrespectful behavior, bullying, or inappropriate comments, also in the discussion forum, I will report this. So be honest and be respectful, and then we have no problem. Okay. Any questions at this point? Good. Then for the, just wanted to ask, do you prefer having now a little break or now finishing the material and we stop earlier? So who wants a break? Who wants to continue and finish earlier? Very good. Some are still indecisive, but the majority wants to continue. Okay. So it seems to be not overwhelming so far. In general, I tend to speed up when I talk, and the best way to slow me down is to ask questions. Let's see if we have a few here on the chat. So one question here is, will edge machine learning deployment be discussed in this course? I'm not sure what you mean by edge machine learning deployment, but as I mentioned before, we will mainly discuss mathematical models. So we will not talk about low-level implementations of federated learning algorithms. Another question, are there any predefined projects or we should define a project for ourselves? At the moment, I'm not leaning towards preparing a list of topic ideas. I want to make it also a bit of a challenge for you to come up with a good choice, a useful choice. So there will be no predefined, most likely there will be no predefined project list or project topics. Okay, so let's jump into the fray of the actual course content. So this course is called Federated Learning. Then it might be good to first talk about what is federated learning. And my one-sentence definition of federated learning, which I hope you will fully grasp after this course, is as follows. Federated learning trains machine learning models in a distributed fashion over a network of devices. So we have here in this sentence machine learning models. So it's a special type of machine learning, or you could view it as an upgrade of machine learning, which uses networks. So it's bringing in communication networks. It's binding together communication networks or networking ideas and machine learning, training of machine learning. In a sense, it's distributed optimization of machine learning models. And I have shown here one prototype or one example for a federated learning application, which was popular or which was very hip 2 years ago or so when we had something called the COVID pandemic. Maybe some of you remember those nice days sitting alone at home and following Zoom lectures. So we had several apps. So researchers then felt, of course, obliged to contribute and develop apps like COVID tracker apps. And these apps could be seen as a simple form of federated learning. So you train your own model, which is to predict, are you very likely to have COVID or contracted COVID or not? So we want to predict something. And these predictions are based on local observations. So there has been, maybe some of you have heard this cough detector app. Was it from Cambridge? They developed a machine learning system that analyzed coughing, when you cough. And the recording of it was analyzed if you have COVID or not. I don't know if it took off. I have not followed it further. But this is one machine learning problem. But to improve it, you could couple these cough detectors over a network of 1 million people. And this kind of scaling up, this using collaboration between many machine learning models, this is one of the key aspects of federated learning. So we want to collaboratively train personalized models by exploiting similarities between many small chunks of data. Yeah, some key characteristics of federated learning are that we have no centralized data collection. So this gives some form of robustness, because if you have a server-based system, if you kill the server, the system doesn't work anymore. In this course, you will hear about fully distributed peer-to-peer federated learning algorithms. So if you take on one of the peers, the network will still continue with other peers. So it's like a self-healing property of these federated learning systems. Yeah, another key characteristic is this personalization of models. So each model or each device in a federated learning network, in a federated learning system, trains a personalized model. So this means I can train a model that is really tailored to me, gives me the optimal prediction. How long does it take me to get to Campi when I start now? When I take a bike, I don't want to have the average prediction. How much does it take for an average person cycling from here to Campi? I want to have the tailored prediction. How long does it take me, given my current fitness condition, my bike, the road conditions currently? I really want a tailored prediction. And this is something that federated learning can do if you have suitable, if you have the federated learning system designed accordingly. So there's a personalization aspect in federated learning, and then there's the scalability. So instead of only using my history or my cycling history, I can use the information contained in the cycling logs of millions of users. So how many of you have a fitness tracker or used a fitness tracker? There's a company called Polar, I think, in Finland. I'm not paid by them. I just remember their name. And I assume, if I remember correctly, they have also apps. And via these apps, they collect all kinds of fitness traces. Whenever you run, Polar gets a bit more data that it can use to train a better predictor for how long it takes me to get to Campi. Okay, and it's maybe the most widely known characteristic of federated learning is the privacy. So no raw data is shared, only model parameter updates or some other derived quantity. It doesn't need to be model parameter updates, can also be something else, because in this course you will learn how to do federated learning with non-parametric models. And for non-parametric models, you don't have model parameters. So you don't exchange model parameter updates. You will exchange something else. And this you will see in a later module, what we exchange. Okay, here's another question. We had the CoWIN app in India, which had this distance thing. Okay, that's just a comment. Thanks for mentioning this. CoWIN app. I didn't hear about this before. Then another question, if the model is being trained on data from various users, how is it personalized to one user or each user on their device? Very good question. So this is a bit of contradiction. So we share the information. We share the information among devices, but at the same time, we train a personalized model. And this is something that federated learning can trade off. So you will hear about federated learning systems that know how to combine the information from other users. So which other users have similar characteristics to me? For example, have the same body mass index as me or the same cycling training level. So this federated learning algorithm, they know which other information to pick to optimally train your own personalized model. Very good question. Okay, another question. There's a question, what does it mean non-IID data? Where is this non-IID data? I didn't mention it here. I guess the question refers to another module. I will talk more about non-IID in a later module, but not in this intro lecture. Okay, so federated learning applications, a quick overview. Federated learning is one of the hot topics or buzzwords in machine learning, gaining more and more traction in applications beside healthcare. So I would say maybe healthcare was the first main application. There really federated learning took off some 8 years ago. But now you find it in mobile networks, so you can use federated learning to optimally steer base stations, to optimally allocate resources in mobile networks. You can use federated learning for cybersecurity. So each server or each node in the internet trains a machine learning model to detect cyber attacks. In autonomous vehicles, so each car, electric car, I don't say any brands, each car can train its own machine learning model for obstacle detection. And these individual models could help each other. So if there's one well-trained model and I pass by this car with my own car, why not exchanging this information so my model all of a sudden becomes better in obstacle detection? Yeah, I have put here more examples, but I really I look forward already to the projects where I see all your federated learning applications. So I will skip those here maybe. Yeah, for the lecture parts, to illustrate some of the concepts, our running example will be the weather. I really like the weather. It's such an innocent topic and a good data source. So we will use the federated learning application of the Finnish Meteorological Institute. So here we have weather stations, and you will learn how to analyze this weather data in the assignments, to read in this weather data. This is only a subset. I think in total there are some 200 weather stations all across Finland, and you could then try to train a forecasting model for each weather station or for the neighborhood of each weather station. Sorry. Just a technical glitch, which is good to slow me down so I can check the questions. Nothing new here. Okay, so we can train a different or a separate forecasting model, for example, for the Kuusamo area, another model for the Inari area, another model for Enontekiö. And this might make sense because the dynamics of weather in Inari might be very different from the dynamics of weather near Turku. So you will learn how to use federated learning to optimally combine the information in all these weather recordings. And this is nice about the FMI. It really has a nice data interface, so you can read in this weather data using Python scripts. And all this information in this local weather data can be combined to train optimal weather forecasting systems for each of these locations. Another nice example of open data. Yes, one question.
So if I were to nice to just say no, coding instead of train a lot of machine learning, just train one.
Yes. Yes. So the question was a standard machine learning approach would be to just define more features for the weather stations, so to include the location of the weather station, the latitude and longitude as features of a data point. And then you just scrape, you download all the data from all FMI stations and use one single deep neural network that also uses the latitude and longitude as features. Yes. Okay, then another example of distributed data and distributed machine learning problems, Finnish road safety. So I also found out that you can download the current or the most recent snapshots of road cameras, weather cameras operated by FinTraffic. And you could say the weather, the snapshots of the weather cameras over the last 10 hours is the local data set for one node in a federated learning network. And you would like to predict, for example, what's the risk of having a congestion here during the next hour? And of course, these data sets are interconnected somehow because there's a underlying road network. So if you have a congestion here in Raunua, you might have a bit later congestion here also nearby in Oulu, somewhere near Oulu. So there are some intrinsic similarities between the statistical distributions of the data sets, and we will see federated learning algorithms that exploit these similarities in the statistics. There's one question in the FMI example. We can train separated models, can't we? What are the advantages of federated learning? Yeah, so very good question. Why not? Why not training a separate model for each weather station? It could be the best. So it could be that we have enough weather observation in Lieksa, for example, and the weather distribution is so different from all other weather stations that it doesn't make any sense to collaborate. So it might be that for some applications, the best thing you can do is independently train a separate machine learning model for each local data set. There might be applications where this is the best way to do it. However, if you have very small data sets, and in particular small relative to a model that you want to train, for weather forecasting, we now use deep neural networks with billions of parameters. So this means that a data set with 1 million data points is small. So for small local data sets, relative to the dimension of the local model that you want to train, you don't have enough data on one client. So you need to pool somehow the information from several local data sets. But you must pool them in the right way. You should not pool, for example, data from the coastal weather stations, which have a very different statistical distribution, as I understand. Okay, just one final example for an application is the Internet of Things, and this is growing fast. So I found here some numbers from Ericsson, which is the Swedish Nokia. So we have around billions of interconnected IoT or IoT connections, and you could think of each device in an IoT network as running one simple machine learning algorithm. So how do we coordinate, or how do we make them collaboratively train their models? Okay. Any questions at this point? No. Let's look at the chat. Chat is gone. Okay, so how do we get from machine learning to federated learning? So basic machine learning is to train a single model by minimizing the average loss on a single data set. So how many of you have implemented machine learning training in Python? Yes. So, but no worries if you didn't do it. We will have a short refresher in the first assignment. So this just to bring you onto speed, that we're on the same page. And the difference now between machine learning and federated learning is you train a separate model for each device. So all of a sudden you're not having so this is the prototype of a Python implementation of a machine learning method. So you read in data, store them in an NumPy array X and Y, you choose a model from some library, and you hit the .fit button, you run the .fit function. That's basic machine learning. So what's the difference? In federated learning, we now do very similar. It looks very similar. Actually, it looks exactly the same in each node. So where do you think is the coupling here between these machine learning models? So when you implement the federated learning algorithms in this course, the code looks pretty much like this. So where do you think we do the coupling? So we could do it in model.fit. We could bring it in somewhere here. Yes. So it's a tough question, I admit. But the idea will be to bring it here in read data. So we will instead of reading in just the NumPy features X and Y, the features and the label, we will also read in data from other devices, which, for example, have an IP address. So all you need is an IP address and then set up an IP socket to it. But forget about these details. We will not discuss this IP socket programming in any detail in this course, but just one idea how to implement this coupling. And this read data function gets some summary statistic from the other node. So they exchange some summary statistic. And one form of a summary statistic could be a model parameter update, but that's only one form. You will see other statistics that we can exchange. The important thing is we will never share the raw data. We will never share this X and Y that we get in here with this node. We rather share some model parameter update in this read data function. Okay, there are some questions. So there's one question. We could use federated learning for air quality analysis as well. Yes, that's one possible application for a project. So instead of one big machine for each sub-district or one big machine learning model, we could use one for each junction. Does that count as federated learning if we're trying to build a model for that? Yes. So this would be a very cool federated learning application, air quality prediction or air quality forecasting. Next question, how hard it's gonna be to secure the global model in federated learning, as a malicious node might trigger data from local node to global model? So we will talk about robustness against data poisoning in the last module, in module 6. So I will briefly touch methods to make federated learning robust against some malicious nodes who intentionally perturb data. Then another question, I have heard that in federated learning, the model is initialized at the central server and then distributed to the clients. Can different models be distributed to the clients? So in this course, we will mainly talk about fully distributed decentralized algorithms, where each node starts with its own initialization. So there's no initialization needed from a server. Next question, how federated learning can handle participants' instability, for example, in vehicles. I mean, in some cases, we have various participants. In these cases, will the result be reliable? Very good question. So this is related to robustness. So we need to make our federated learning systems robust to devices that don't behave as expected. For example, because they are run by an Austrian cybercriminal, or something is wrong with the device. It just doesn't work and spits out random numbers. So we should develop, so trustworthy federated learning systems must be robust against, to some extent, against such failing nodes, so to say. Next question, very good question. Is federated learning similar to transfer learning? Yes. So in a sense, this federated learning methods are a form of transfer learning. We transfer the knowledge from different devices to other devices. So it's a special case of transfer learning, or a specific form of transfer learning. Very good question. Next question, do we choose our models in each device based on each client data? Yes, so the model that we use, for example, here in this example, if we use SGD regression or here decision tree, this is a design choice. And in principle or in general, this design choice is based on the local data statistics. So you must somehow know if you want a decision tree or somebody requires you to use a decision tree. For example, because decision trees are transparent or easy to understand. So this is a design choice. Each client can choose its own local model. Next question. How do we average the model weights while models are not the same? Very good point. So in this course, you will learn methods where you federated learning methods that can cope with completely different types of models. So you can have one node which runs a decision tree and another node which runs a deep neural network or linear regression. And you will see how to combine those models, not by model parameter updates, but by something that is similar to knowledge distillation. So you will see how to couple those models by forcing them to have similar predictions on a common test set. But you will hear more details about this in module 3 and 4. Next question. Can a node help another node to train its model because of computational power? Yes, so it might be that one node has so much computational power that it can train the model much faster than others and get better predictions on a test set, which is then shared. This knowledge is then shared with other nodes which run slower, which have less computational power. So in a sense, these federated learning algorithms allow also to leverage computational power of neighboring nodes, not only data or not only the information in the data, but also the computational advantages of other nodes. Very good questions. Next question. If the models are introduced at clients, how can we ensure the consistency in aggregation of model parameter update parameters, because different clients can initialize different models? Yeah, as I said, we will discuss this in module 4. We do this by a form of knowledge distillation. So we never compare, or we don't compare model parameters. We only compare predictions of models on a curated test set. So the different models should somehow agree on a carefully chosen set of data points. That's how we couple the models. Next question, how is federated learning different from decentralized machine learning? I don't know what exactly is meant by decentralized machine learning. I would say federated learning is one form of decentralized machine learning. Next question, is it possible to reverse engineer or infer private data from shared model parameters such as gradients or weights? Yes, yes, that's possible. That's known as a model inversion attacks. So model inversion attacks, they just observe, for example, what was the model parameter update shared of this node here with that node. And just from knowing the model parameter update or a gradient, it might be a gradient, this node can find out a bit about the local data set here. To some extent, this is possible, yes. And we will have one assignment. Think assignment 6. You will try out a method that allows to infer some properties of the local data set just from the model parameter updates. Next question, can data-specific aggregates be shared across devices in this setup? I'm not sure what is meant by data-specific aggregates here, so I need to skip this question. Sorry. Next question, how the federated learning model would provide compatibility, like backward compatibility, as different nodes might have different resources. Good question. So I don't know how to answer that. As I said, in this course, we mainly ignore implementation details. So as long as we can compare the model predictions on a test set, we can use this device or the machine learning algorithm running on that device. Next question, is federated learning used only in the training or also in inference? So in this course, we focus on the training phase. We focus on federated learning algorithms that are used to train machine learning models. And once you have trained a machine learning model, for example, for this node here, you just use it on this node for making local predictions. So these predictions, the prediction step is then fully decoupled. We only use the coupling for the model training. Okay, so just to finish my last few slides, from a mathematical perspective, we can think of federated learning as a tensor product. I like this tensor product concept of machine learning. So instead of having one single machine learning problem, which is to fit a curve to data points, we have now a whole collection of machine learning problems. So a whole collection of data sets and different curves, which might come from different models. So here we have a linear model, here we have a polynomial model. Yes, but more details about how we couple these individual machine learning tasks will be provided in the next lecture, next Monday. I just want to finish this lecture, let's say with 5 minutes of a machine learning refresher so that we're all on the same page. So I apologize for those who have seen this already 1,000 times. So what is machine learning? Machine learning is about learning a hypothesis map. It's about learning a function. For example, I want to know for a certain user, given a certain mood and daytime, what is the best song that I should recommend to the user to uplift his mood. And this might seem like a toy application, but I have found actually a recent work on how to choose the right songs or how to use music to treat depressions. So we might train a model, and if we solve this problem well enough, we might get rid of medical treatment of depressive disorders, which might be, of course, a loss for Orion company in Finland. And mathematically, as I said, so machine learning is about fitting a curve to a bunch of data, which we call training data. So we want to fit a curve to these blue data points, which we call the training set. We want to minimize this average loss. And after we train a model, this is very important, we always need to validate the model. Never, ever stop after training a model. Because with modern models, powerful deep neural networks, you will get a small training error. Then you might think, wow, I have now trained a super good model. You run to your boss or colleague and brag about your cool model. And then the colleague asks you, and what is the validation error? So how is the model doing outside the training set on which you have optimized your model? And this is then the hard truth. So you might get a very small training error just because you have such a big set of possible hypothesis maps that by accident just fit your training set, but they do very poorly outside the training set. Okay. So this might sound trivial, but in the end, I would say it's still the day-to-day job of an applied machine learning engineer. So train a model, evaluate, compute the validation error, and compare it against some baseline or benchmark. So does any one of you know about the principled way to compute the baseline or benchmark? So when do you know that the validation error that you have obtained is close to optimal? There's no point in pushing this further. Yes? Yeah, so in general, the validation error will be higher than the training error. So what do you do then? You do some regularization techniques to bring it down on the same level. So let's say we have the training error and validation error on the same level. How do you know if this level is good, close to optimum or not? When do you know that you're done, basically? You cannot get better performance. This is related to the question of having a baseline or benchmark. What is the ultimate baseline or benchmark for the performance of a machine learning model? Does any one of you work as a machine learning scientist or researcher? So when you work, let's say you come up with a cool new network architecture, call it transformer networks, and you apply it to some data set and you train it and you get a good performance, like validation error, small like training error. When do you know that this is really good now? This is something you should share with others in the community. Submit the paper to NeurIPS. Compare to state of the art. And how do you compare to state of the art? You read papers, yeah. So that's maybe the main source for a baseline is state of the art, reading papers, or do you know other sources for baselines for the state of the art than reading papers? Leaderboards. Do you know a platform where there are leaderboards for papers with code? Or do you know Kaggle? Is this still a thing? Maybe I'm too old already. I was amazed about this Kaggle. And this, I would say, is one of the key drivers for the machine learning explosion or the machine learning research explosion, because we have these leaderboards. We have well-defined benchmark levels or benchmark data sets where you can compare your proposal for a new transformer network architecture with others. And if you beat it, you submit a paper. Okay, do you know any other way to get a baseline or benchmark besides comparing with what others did previously? Yes. Could you repeat? Compared to a human, yeah, human performance. So you might just say, you might set a performance target, or you might have a regulation. Like I hope that this autonomous vehicles, they have a regulation that requires if you have one accident in 100,000 hours of driving or so. So this defines a baseline. How much errors, how much wrong predictions can you tolerate? Yeah, I also mentioned another one which I like because my background is in applied statistics, which is the Bayes risk. So if you know a probability distribution of your data, you can compute the optimal error level, which is called the Bayes risk. But the drawback here is you need to know the distribution of the data, which we rarely know. Okay, so what can we do instead of making these cycles? So come up with a machine learning model, train it, compute the validation error, and if it's not good, retrain it. Well, in practice, we could do regularization. So this picture here, when the validation error is larger than the training error, is a typical situation when you train a powerful model, because these highly or high dimensional models, they allow to achieve a small training error, but you will overfit. And you will overfit typically when the training set is not large enough, is smaller than the dimension of the model. So what you can do is you either increase the data set size or you decrease the model size. And this is what you do when you regularize a model. So there are three different perspectives on regularization. The first perspective is you increase the data set using data augmentation. And the idea is you typically know some intrinsic symmetries or invariances in your data. Like when you have a feature that is measured by a sensing device, then it's typically subject to noise. Maybe some of you have sometimes looked into data sheets for a temperature sensor. And this temperature sensor data sheet tells you this is accurate, this measurement is only accurate up to plus minus 1% error. So in everything you measure, there's typically an uncertainty, a measurement error. So why not saying then, okay, instead of this blue data point, I could have equally well observed these perturbed red data points. So you add a bit of noise to the features of the data point. And all of a sudden you have 3 data points instead of 1. And then you not clone it 2 times, but you clone it 1 billion times. Each time adding a random realization of a random variable. So you can arbitrarily increase your training set using data augmentation. So this is one approach, and it turns out that this approach is actually equivalent to adding a penalty term to the loss function, because this augmented data points, the effect of these augmented data points is to add terms to the loss function, to the training error, and you can collect those additional terms as a regularization term, and this is just a penalty. And you can show, for example, that this rich penalty is exactly what you obtain when you perturb each data point by a Gaussian random variable infinitely many times. And you will actually, in the first assignment, you will have to implement this. So I find this a cute trick to implement such a penalty term, a rich penalty, using a data augmentation. How many of you have ever implemented a rich penalty or rich regression? Very good. How many of you have implemented rich regression or rich penalty for decision trees? Yes? Now you crushed my joke. How? So is there an option in scikit-learn for decision trees to implement this type of rich term? Because in decision trees, you don't have a model parameter vector. So it's not obvious how to implement, what is the analog of this rich term that you can use for linear regression or anything that has a parameter vector. But what is this? How do you implement this for a decision tree? And in the in the first assignment, you will learn how to do this, how to implement an analog, or how to generalize this rich penalty term to decision trees. And the idea is this rich penalty is exactly what you would get if you add, in a deterministic way, new data points to the training set. So you can obtain this rich penalty term by adding specific data points with a specific label. In particular, you set the label to 0. And when you work out the additional loss on this augmented data set, this additional loss is exactly this penalty term. And I find this trick cute because it will also allow us to implement federated learning algorithms. Because, I mean, this is maybe the summary of the whole course, or the idea of the whole course. In federated learning, we construct this penalty term using the predictions of other models. So instead of perturbing the local data set, we use the predictions that we would get from a neighbor node or from another device on our data set as augmentation. That's how we couple the models. And the nice thing is that this does not rely at all on model parameters. So you can do this with any kind of model as long as it delivers predictions in the same label space. So if you have regression models, then you can couple any regression models that you like: decision trees, deep neural networks, linear models. Okay, and that's it, actually. That was a nice conclusion of today's lecture. So today we talked about the course logistics and schedule all the activities. And finally, we started to talk about how to do machine learning, how to regularize machine learning. And in the next module, we will see how to scale up this machine learning setting to networks of machine learning problems. I call this federated learning networks. This is a mathematical object. It's basically a network model with some machine learning on top of it. And so this will be the next model next week. And in the later models, we then use this federated learning network to formulate optimization problems, which are like federated learning problems. And then we solve this federated learning optimization problems using optimization methods, which gives us a very clean and principled approach to design and crank out all kinds of different federated learning algorithms. Okay, any questions at this point? Very good. So on the chat, one final question I will answer. When can we access this lecture on YouTube? I would say within the next 10 hours. So I will translate this, I will transfer this recording onto the YouTube playlist.
Check it with some person.
I have it already. Okay. Okay, thanks a lot and have a nice evening.